Hey everybody, welcome back. What we're going to do right now is wrap up our discussion of constant motion graphs by putting in two of the more subtle and kind of complicated ideas that you'll need to be able to use these in a really well-rounded way to describe all the different kinds of motion that we're going to see. Before we jump into the graphs, what we wanted to do is to take a look at something. We've been using in class the words vectors and scalars. So you should know that a vector is a number that has a quantity that has a number in a direction, and a scalar is just a plain old number. So for example, if we go looking at something like mass, then mass is just going to be 250 kilograms. That means that's an example of a scalar. But when we see a minus sign in front of weight, which is a thing that we get, by the way, when we take mass and do some work to it that you'll see later in the year, when we see the minus sign in front of the 2,500 newtons, that should indicate a direction. And in this one, they're taking no chances. They've told us it's also down. So where the first one was a scalar, this one's definitely a vector. And we have that same kind of relationship between distance and displacement. So distance is just 20 meters. We don't know 20 meters in what direction. It's just 20 meters. And displacement is 20 meters to the right. Or maybe they would put minus 20 meters. The reason I'm throwing this out here, though, is that it's really easy in class to get fooled into thinking that distance and displacement are always the same number. And you just have to pay attention to, is there a minus sign or is there another word after it? Because it's not always that easy. So I'll give you an example. Here's an example we took a look at in our last video. And what we did was we said that you were starting at a position here. Location 1 was 2 meters from the origin. So there you go. And then you walked on out during transition A to a place that was 10 meters from the origin. So if we just focus on that, and we'll go and get the displacement, the change in position there for those two was 10 meters minus 2 meters. It was a displacement of positive 8. So you moved 8 meters in the plus direction as you did this transition A. Okay, fair enough. We should all be good with that. And so here we are, location 3. You walk from position of 10 meters to a position here of 4 meters from the origin, and the delta position is this guy minus that guy, and you get negative 6 meters. And so if they asked you for the overall displacement, if you threw the bracket around A and B and said, if you take them together, what's the overall displacement of A plus B? That's really not tricky at all. The overall displacement would be, you'd have positive 8, and then you'd add it to a negative 6, and you'd see that the overall displacement was positive 2 meters. Well, you could see that if you looked. We started at 2 meters from the origin, and we ended up out here at 8 seconds, 4 meters from the origin. So yeah, it looks like we moved positive 2 meters. However, what's the overall distance that you covered? Are you going to slap an absolute value sign around this 2 and say, oh yeah, the distance we covered is just 2 meters? That'd be wrong. And here's why it'd be wrong. Because in this section of the graph, section A, you moved 8 meters. So you had plain old 8. And then in this section of the graph, we moved negative 6 meters of displacement. But really, that's a distance of 6. And you should feel pretty comfortable saying, oh yeah, that makes sense, that the distance that was covered overall between A and B was actually 14 meters. So that kind of stuff is going to make a huge difference when you start covering regions, when you start blanketing A and B. So we'll show you how that works for velocity and speed, and show you how different the answers can be. So to get average velocity, so average is telling you to throw the brackets around all of it, so A and B. So across the entire graph, what we're going to do is just remember what we did a second ago, where when we got the displacement total, we figured that positive 8 plus a negative 6 gave us positive 2 meters of displacement. And that took 8 whole seconds to accomplish. And then we get an overall average velocity of plus, looks like a quarter, 0.25 meters per second. Okay, so that's average velocity for the region of A and B. And there's no way that the average speed is going to be the same number. because what we have to do is feed in the right numbers. The total distance for this guy was 14 meters, if you remember. And yeah, I know it took 8 seconds, and we'll divide those two things. And I think what we're going to get is 1.75. Is that right? I feel like that's right. I'm doing it without a calculator, but 14 over 8, 1.75. Yeah, that's right. Okay, so there you go. So average speed, average velocity. Make sure you look across the entire breadth of the graph, and that you handle them the right way. Okay, so bring your questions to class. Take care. Good to see you. Bye-bye.